Well, I'd like to welcome you all to this special Provost lecture that's co-sponsored by the Pratt School of Engineering and the School of Medicine here at Duke. It's wonderful when I look out in the audience, as much as I can see, to see so many faces, not only from the university, but also from the wider community of Durham and the Triangle. I think this is a real testimony to the inspiring and impactful work of our speaker, Blake Wilson, the co-inventor of the cochlear implant technology that has enabled hundreds of thousands of people worldwide to hear. I was actually telling Tom Katsileas right before I came over here, I watched again the video that was put out when Blake won the Lasker Award, and I have to say it's one of the most moving examples of the human impact of wonderful science and wonderful engineering. And so I think it's going to be really exciting to hear Blake's description. And also, as I said, very moving. This is the first lecture I've hosted since becoming provost, and I really can't think of a better speaker than Blake to represent what this university stands for: to create and apply knowledge in the service of society. And of course, we're especially proud because Blake is both an alumnus and a faculty member at Duke. You probably all know that this lecture also commemorates the 75th anniversary of the School of Engineering at Duke. The school has trained thousands of engineering students over the years, including Blake, as I said, and has also conducted groundbreaking research to solve many of society's most challenging problems. So I'd like to kind of have everyone join me in a round of applause for the Duke engineers. Again, for the many contributions they've made to the world, again, including the one that we're gathered here to hear about tonight. With that, I'd really like to turn the podium over to Tom Katsileas, Dean of the Dean of the Pratt School of Engineering, who will introduce our speaker formally. So I hope you enjoy the lecture. Thanks.
Thank you, Provost Kornbluth. And thanks to everyone in the audience for braving the wintry mix to come out this evening and the parking. It's a pleasure to see so many of you here from across the university. I'd like to especially recognize and thank my colleague, Dr. Nancy Andrews, Dean of the School of Medicine, for co-sponsoring tonight's lecture. Thank you, Nancy. So as the Provost mentioned, this event commemorates the 75th anniversary of engineering at Duke, so you might wonder why the Provost's Office and School of Medicine are co-hosting the lecture. Well, our university is known for transcending academic boundaries, and so is our speaker tonight. Blake Wilson is an electrical engineer, and we are extremely proud to count him as a distinguished alumnus of Duke Engineering. But his ties across the university are many and strong. He holds professorships in both the engineering and medical schools, co-directs the Hearing Center, the Duke Hearing Center, and collaborated extensively with colleagues across the university during his 33 years at RTI, the Research Triangle Institute. Over the course of his career, Dr. Wilson has focused on engineering solutions to a challenging medical problem, making it possible for the deaf to hear. By designing innovative strategies for processing sound waves, he played a key role in developing the modern cochlear implant, a technology that has enabled hundreds of thousands of people to transcend boundaries of their own, from a world of silence to the world of sound. His work represents the first of the human senses to be restored by a prosthetic device. So in that sense, it is a landmark in the history of engineering as well. Last week, I was honored to be present at the National Academy of Engineering when Blake Wilson and several of his colleagues from around the world received the 2015 Fritz and Dolores Russ Prize. The Russ Prize is considered the top prize in the world for bioengineering, given every 2 years for advances that significantly improve the human condition. Just a couple of years earlier, he received the 2013 Lasker DeBakey Clinical Medical Research Award, another of the world's most respected science prizes. While I was at the Russ Prize ceremony, I had a chance to talk with Michael Merzenich, a neuroscientist and a member of the team being honored. Dr. Merzenich noted that the development of the cochlear implant was a long-term project to which many people contributed: engineers, audiologists, neuroscientists, physicians, and more. But he called Blake Wilson's contribution singular, because although many people were on parallel tracks contributing similar advances in hardware, Dr. Wilson's signal processing breakthrough stood alone in its transformative effect on performance, particularly in the area of improving speech recognition. Despite the potential commercial value of his breakthrough, Blake Wilson chose to make his discoveries freely available for both academic and commercial use in order to speed the new technology from the lab into the clinic and into the lives of people who could benefit most. So you can see that Blake Wilson is not only a singular engineer, but a singular human being. It is a privilege to have him represent our schools and our entire university as the Duke Engineering 75th Anniversary Distinguished Lecturer. Please join me in welcoming Professor Blake Wilson.
Wow. Thank you.
Thank you so much. You honor us. Break a leg.
Okay. Well, thank you for that lovely introduction. Wow. And seeing all of you here makes me feel great. Thank you for braving the weather. I have many friends in the audience and many people who have worked with me and our teams to develop the cochlear implant. This lecture is especially meaningful to me because my father graduated from the engineering school in 1947. And he's shown in the slide. He served with great pride and distinction in the Navy immediately after Duke. And among his classmates was Edmund T. Pratt, for whom the school was named in 1999. So there are the many connections that Dean Katsouleas mentioned, and this connection with my father. So in my talk today, I'll describe the development of the modern cochlear implant and the first substantial restoration of a human sense using a medical intervention. And in my view, there were 4 large steps forward that made the present treatments possible. The first step was to develop devices that could be used for a patient's lifetime. These were relatively simple devices by today's standards, using a single channel of sound processing and a single site of stimulation in or on the cochlea. And they provided an awareness of environmental sounds and some help with lip reading. The next large step forward was to provide multiple sites of stimulation in the inner ear. Our normal inner ear responds differentially to different frequencies depending on the site of maximal excitation. So to mimic this so-called tonotopic organization, you need multiple electrodes within the inner ear that can stimulate subpopulations of neurons more or less separately. This is a very difficult thing to do, as I'll describe a little later. The next large step forward was to utilize those sites better than before for representing sounds and speech information in particular. And this was a large step forward that enabled most recipients of cochlear implants to understand speech in everyday situations. And today, more than 80% of adult users of cochlear implants use their cell phones routinely. This is a long, long trip from total or nearly total deafness to chatting on the cell phone, something we never could have imagined at the outset. This was a quite happy and surprising outcome. The final large step forward, at least to date, was to provide stimulation in addition to that presented by a cochlear implant on one side. And this can be done in one of 2 ways. One is to provide cochlear implants on both sides, so you have electrical stimulation on both sides rather than one side. And this can reinstate a sound lateralization ability and other benefits. And the other way is to present acoustic stimulation for persons who have some residual hearing at low frequencies and use both modes of stimulation, and this is quite valuable as well. So today, the cochlear implant enables wonderful family connections and normal conversations for the great majority of users. It didn't start that way, as I mentioned, but today, Bill Gates Sr. can talk with his son with ease because of his cochlear implant. And you can see the external components of the cochlear implant immediately above and behind Bill Gates Sr.'s ear. Around his ear, there, is a sound processor that includes a small computer to analyze sound and make decisions about what stimuli should be delivered to the implanted electrodes in his inner ear. And these are also called sound processing strategies, as I'll describe in a moment. And above that is a radio transmitting coil that sends encoded information across the skin to an implanted receiver stimulator that decodes the radio transmission and generates the stimuli to be delivered to the electrodes in the cochlear implant. So I'll say a little bit more about the components of cochlear implants. I'll describe the function of cochlear implants. I'll say a little more about the history, especially steps 2 through 4. I'll indicate where we are today and the remaining distance between electrically elicited hearing and normal hearing, a gap that's ever closing. I'll mention a few impacts of the cochlear implant on society and the individuals that use them and their families and coworkers, and then I'll offer a few concluding remarks at the end. So the internal components of a cochlear implant system are shown along with the external components in this slide, where I've already described these two external components. Beneath this radio transmitting coil is a radio receiving coil and a set of electronics in a highly compact integrated circuit that decodes the information transmitted across the skin by the radio frequency link and then generates stimuli that are conveyed by a cable down to an array of electrodes coiled around the helical structure of the inner ear. These electrodes are inserted into a chamber of the inner ear called the scala tympani. It's the lower of 3 chambers that run along the length of the uncoiled inner ear. That is the most surgically accessible among the chambers. And here you can see 12 sites of stimulation within the inner ear. This is a tremendous reduction compared to what we have in normal hearing, where we have 3,500 inner sensory hair cells along the length of the cochlea, and we have 30,000 neurons in the healthy inner ear. So you can appreciate that there's a tremendous reduction in the details of the representation provided by a cochlear implant. So on the left panel are cartoons of the normally hearing ear and the deafened ear, the normally hearing ear in the top panel. And you can see the 3 small inner middle ear bones that convey sound vibrations from the tympanic membrane to the fluids of the inner ear. And these fluids, the vibrations in the fluids, launch what's called a traveling wave of displacement along a structure called the basilar membrane, which is very narrow and stiff at the middle ear end and wide and flaccid at the other end. So these mechanical properties give rise to a tuning ability where high-frequency sounds preferentially stimulate this basal end of the basilar membrane, and low-frequency sounds the other end. Along the length of the basilar membrane are these sensory hair cells that I mentioned before, which can be stimulated by movements of the basilar membrane that shear the cilia of the hair cells, which in turn releases chemical transmitter substance into the cleft between the bottom of the hair cells and adjacent fibers of the auditory nerve, which excite the nerve fibers and in turn excite auditory structures in the brain. Turns out that these sensory hair cells are extremely fragile to a variety of insults, including loud sounds, various genetic defects, ototoxic drugs, drugs that are poisonous to the inner ear, and they are the principal cause, their loss or destruction is the principal cause of hearing loss or, in severe cases, total deafness. In contrast, the neurons are far more robust than the sensory hair cells. So the concept of a cochlear implant is to bypass these damaged or missing hair cells and stimulate the auditory neurons directly with electrical stimulation rather than the chemical stimulation that we have in normal hearing. This right panel shows an expansion of the business end of a cochlear implant, and here you can see a little better the 12 sites of stimulation. Present-day cochlear implants use between 12 and 22 sites of stimulation. So in this deafened ear, the survival of the sensory hair cells is sparse or totally absent. And these different electrodes are stimulating different positions along the length of the cochlea to excite the adjacent auditory neurons. Before describing a little more about the history, I should start at the beginning and say that at the outset, skepticism was very high. Nearly every expert in auditory physiology or otology, ear surgery, thought that reinstatement of useful hearing with crude electrical stimulation was a fool's dream. And you can see that many of the comments were categorical. For example, the eminent auditory physiologist Rainer Klinke in Frankfurt said, from a physiological point of view, cochlear implants will not work. Well, that was in 1978. That wasn't that long ago. And the criticism continued after that. When I started my work, I got a lot of career advice about not entering this field because all the experts said that the cochlear implant couldn't possibly work. And their argument was based on the complexity of the inner ear. It's an exquisite structure with many interacting components. And how could one have the hubris to think that you could somehow replace this elegant machinery with broad, pervasive electric fields in this small structure of the inner ear? But fortunately, the pioneers persisted, and we have the wonderful devices we have today, despite this initial criticism. Lots of people ignored the criticism, and the development of the cochlear implant was a worldwide effort that included teams initially in San Francisco, Palo Alto, Los Angeles, Salt Lake City, Paris, Antwerp, Vienna, and Melbourne, Australia. So these lines, the light lines, show the onsets of experimental studies to develop a cochlear implant, and the thicker lines show the development of clinically applied devices. So the line of experiments, in many cases, is rather long. The symbols show the contributions by each of the teams. For example, step one was largely achieved by Dr. House in Los Angeles. And the double S symbols show the development of multisite implants, for example, by Don Eddington and his team in Salt Lake City. These efforts proceeded in parallel, as Dean Katsalais mentioned, and each of the efforts produced important results, but even as of the late 1980s, speech reception with cochlear implants was impossible for most users. Some of the key advances in the development of multi-site implants were made by the teams in Palo Alto, Vienna, and Melbourne. And Blair Simmons in Palo Alto made a fundamental discovery early on in 1965, where he implanted an array of electrodes directly into the trunk of the auditory nerve, inserted at different lengths for each of the 6 electrodes, and found that when he stimulated one electrode at a time at different rates, the perception of pitch changed for this research subject, but only up to a certain point. So if he presented 100 pulses per second, the patient always said, oh, or the research subject always said, oh, this is like a foghorn or a low frequency sound. And then when he presented 200 pulses per second, the patient said, oh, that's higher pitched, more like a horn maybe. And when he increased the rate to 300, he said, well, it's a bit higher still, and further increases didn't produce any further increases in pitch. He also could produce different pitches by stimulating different electrodes at the same stimulus rate. So if he presented 500 pulses per second to each electrode in turn, each of those electrodes in turn elicited different pitch percepts. Well, there was a raging debate in auditory neurophysiology at the time as to what code the brain uses to infer frequencies of sound in the environment. One camp said that place of stimulation was most important, the second finding of Blair Simmons, and the other camp said that the nerve cadences elicited by different rates or frequencies of stimulation were most important to the brain. Well, Blair showed that they're both important and that they both operate, and he demonstrated the ranges over which these two codes operate. Ingeborg and Erwin Hochmeyer developed the first microelectronic multi-site implant, which was implanted by Professor Kurt Burian in Vienna in December 1977. That wasn't that long ago either. And then Graham Clark in Melbourne, Australia, developed a similar device that was implanted 6 months later. Graham Clark and his team also conducted many fundamental studies that provided the foundation for to provide the foundation for the modern cochlear implant. So I mentioned before that speech reception was not possible for most users of cochlear implants even as late as the late 1980s. And the status of the field is well summarized by a principal conclusion from a consensus development conference conducted at the National Institutes of Health. These consensus development conferences are conducted by the NIH to offer advice to physicians in the United States as to optimal treatments for different conditions. So there have been consensus development conferences on most every topic you can imagine, such as cardiac problems, cancer care, and so forth. The first consensus development conference on cochlear implants was held in 1988, and the two principal conclusions from that were first that multi-site stimulation probably was better than single-site stimulation, and second, that about 1 in 20 users of cochlear implants at the time, even the best cochlear implant systems at the time, could understand conversational speech without lip reading. In the right panel are shown results from two very simple tests by today's standards with the best subjects selected for each of the implant devices. And you can see at the far right, even the best of the devices produced only about 30% correct sentence recognition with hearing alone. This is not sufficient for supporting a conversation without lip reading. And the circles show scores for the individual subjects. The green circles show scores for subjects who score above chance on a particular test, and the red circles show scores for subjects who score at chance. And you can see for a multiplicity of the devices that many of the subjects score at chance, even for implant devices as late as the 1980s. You also can see a rather broad distribution of scores for the better of the devices and relatively high scores in some instances. So this would be one of those 1 in 20 patients who could carry out a conversation without lip reading. Let me emphasize, this is a very easy test, and a user of today's cochlear implant systems would score at or near 100% correct on each of these tests. So our story is told in this essay in the special issue of Nature Medicine celebrating the 2013 Lasker Awards. And it describes my path through Duke and the wonderful collaborations we had here and how those collaborations enabled our particular contributions. So this essay provides far more detail than I can possibly provide today, and if you're interested, it's easy to look up. Some of the members of our first team are shown on the left, including Charlie Finley, me, and Dewey Lawson. Not pictured is Bob Wolford, who also was a key member of that first team. And I think he might be in the audience today. You can speak with him afterwards and find out what we did. So we won a series of NIH projects starting in 1983. These were 7 contiguous projects that spanned 23 years and were supported by the neuroprosthesis program at the NIH. And a requirement for the first 2 of those projects was to identify a clinical collaborator for we engineers to work with. And at the time, there were only 3 centers in the United States that had any clinical applications of cochlear implants, and they were all in California, Los Angeles, Palo Alto, and San Francisco. I had been a consultant for the San Francisco team for approximately 4 years before then, and when this request for proposals came out for the NIH projects, I contacted Mike Merzenich there, who Dean Katsouleas mentioned, and asked whether UCSF would be willing to be our clinical partner. And Mike said, well, we plan to respond to this request for proposals ourselves. And so I mentioned, well, that's great, but it wouldn't preclude cooperation with us in the bizarre off chance that we won the competition. Well, that bizarre off chance occurred, and we did all of our initial work with patients in San Francisco, built our hardware and software here in North Carolina, and took it to San Francisco. About a year after the first project started, I got a call from Dr. Farmer here at Duke, who was head of otology at the time, and he said, Blake, I heard that you have this project going in San Francisco. Why not bring it home? If you do, we'll build a cochlear implant program here at Duke, which is exactly what he and Dr. Sabiston, the chair of the Department of Surgery at the time, did. So we moved our laboratory here to Duke with all of this fabulous help from otology and the Department of Surgery. Dr. Sabiston gave us laboratory space in the Baker House, which is shown in the lower right panel, and gave us a generous equipment grant to get the laboratory started. On the left, you see Dr. Farmer with Dr. Patrick Keenan holding or sitting behind one of the first cochlear implant devices applied anywhere clinically. This was an experimental device that was developed at UCSF with our help. These people were wonderful and enabled all of our progress. Also wonderful was the support that we received from the Research Triangle Institute in the Research Triangle Park. Shown here is George Herbert, who was president of the RTI at the time, and he was the person who approved the policy that Dean Katsilas mentioned to donate all of the results from our NIH-sponsored research on cochlear implants to the public domain. This was a bold move. The Birch-Bayh Act had just been passed, transferring all intellectual property rights to universities and research institutes, but Mr. Herbert ignored that and instead said, if we donate all these results to the public domain and the results are good, then they'll be utilized by all of the companies and benefit the highest possible number of deaf and severely hearing impaired patients. So Dean Katsilas gives me the credit, but much of the credit goes to Mr. Herbert. And also Grace Boddy, who was the legal counsel for RTI at the time, who crafted the policy. So our work began in 1983, and we were working hard to improve performance with cochlear implants along with many other teams worldwide, and we made some progress. We developed processing strategies that produced results that are a little bit better than I showed you before in those bar graphs, but not spectacularly better. We got a spectacularly better result with the processing strategy shown here, which was discovered in the Baker House laboratory in 1989. And it's called continuous interleaved sampling. Now this diagram may look a little daunting, but I'll walk you through it. And it's really, in retrospect, one of the simplest approaches for representing sound information with cochlear implants that have been developed to date. And it adheres to what we engineers call the KISS principle, which is keep it simple, stupid. I try to adhere to that every day. So the basics of the strategy are to divide sound into different frequency ranges with bandpass filters. And you have a bank of bandpass filters that might range from 12 bandpass filters to 22 bandpass filters. And this bandpass filter may select frequencies at the low end of the audible range, say from 200 hertz to 500 hertz. And this bandpass filter would sense frequency components at the other end of the range, say from 4,000 hertz to 6,000 hertz. Following each bandpass filter is a sensor for energy variations in that range of frequencies. And this can be done in many, many ways. I've shown the simplest possible way in this slide, which includes two components that engineers call a rectifier followed by a low-pass filter. Well, this low-pass filter selects low frequencies and passes them on, but rejects higher frequencies. And the setting of that cutoff frequency at the boundary that I just mentioned sets the maximum frequency of variations in the energy signal coming out of this block. Now, remember that I mentioned before that implant patients can hear different pitches according to temporal information or rate of stimulation only up to about 300 hertz. So representing higher frequencies at any one electrode doesn't make any sense and in fact could present conflicting cues. So this low-pass filter is generally set at around 400 hertz to pass those frequency variations up to 300 hertz, but nothing more. The range from a just perceptible percept to a very loud percept with electrically evoked hearing is very much smaller than the range we have in normal hearing. So you might have a 10 dB range for electrically elicited hearing, but we can hear sounds ranging up to 90 dB in normal hearing. So with our normal hearing, we can sense from a whisper to a jet engine, which is many millions of times louder. Whereas in electrical hearing, you span that same range with only a 2- or 3-fold increase in the intensity. So you must somehow compress the range of sounds that you have in the environment down to this narrow dynamic range that you have in electrically elicited hearing from, say, 90 dB to 10 dB, that huge difference in ranges that I mentioned before. And this is accomplished with a mapping function that provides an instantaneous compression of these energy variations down to the narrow range that allow cochlear implant listeners to perceive soft to loud sounds in a comparable number of different intensity steps that we have in normal hearing. The output of this nonlinear map controls the amplitudes of stimulus pulses that are ultimately delivered to the intracochlear electrodes. So the amplitudes of these pulses are varying all the time according to the variations in energy in each of the bands. But they don't vary at rates or frequencies higher than about 300 hertz. Higher frequencies are represented by stimulating different positions in the cochlea with the different channels. So the output of this high frequency channel would be directed to the basalmost electrode in the implant closest to the middle ear that I mentioned to you before, which in normal hearing is most sensitive to high frequency sounds. And the output of the low frequency channel is directed to the electrode at the other end of the electrode array, which a position which in normal hearing responds preferentially to low frequency sounds, not high frequency sounds. So frequency information is represented in two ways: by the temporal variations in the amplitudes of the stimulus pulses at each electrode, and by the sites at which the stimulus pulses are delivered. The basic aim of the strategy was to represent in the clearest possible way all of the information that could be perceived by cochlear implant patients, and not make any assumptions about how speech is produced or perceived or about sounds in the environment. A signal processing trick helped with the clarity, and the signal processing trick is to present these stimulus pulses non-simultaneously across the electrodes. So if a stimulus pulse is presented to any one of the electrodes, no stimuli are presented to any of the other electrodes. And if this cycling of stimulation across the different electrode positions is rapid enough, you get a fusion of percepts, just as you do when you're looking at a television set. Actually, the television set is scanning lines along the phosphor of a television very rapidly, so you can't see the scan lines. All you see is a picture. And if these stimulus pulses are presented rapidly enough in electrically stimulated hearing, you don't hear the graininess of the representation. Instead, you just hear a normal auditory percept. But the stimuli are presented non-simultaneously. And the big advantage of this is that avoids direct summation of the electrical fields from different electrodes. So if the electrodes are stimulated simultaneously, you get a complete washout of the representation, or what electrical engineers call crosstalk among the electrodes. You need to appreciate that the inner ear is about the size of a pea, and it's largely filled with highly conductive fluid. And these two factors work against independent stimulation of the different sites along the length of the inner ear. So this little signal processing trick proved to be important in presenting the place information in the clearest possible way. We had lots of cochlear implant subjects coming through our laboratory, highly experienced subjects, and when we first played this processing strategy to them, they would say things like, "Wow, now you've got it," or "Hot damn, I want to take this one home with me." It's at that point we knew we had something. So we tested it formally with subjects who were using that processing strategy and device shown at the far right of the prior bar chart that I showed you, the results from the late 1980s, the best of the available devices at the time. And we searched worldwide for subjects who had the very highest levels of performance with that device. And all of the subjects had at least 1 year of daily experience with that device, but only a couple of hours of experience with the new processing strategy. So their clinical processing strategy was called a compressed analog strategy, and the new strategy was continuous interleave sampling. The compressed analog strategy presented bandpass outputs simultaneously across the electrodes. So most likely some spurious cues were generated by the interference among the electrodes, and certainly the independence among the channels was degraded with that simultaneous stimulation. So with these highly experienced cochlear implant subjects, we had first the group that had high levels of clinical performance, at least at the time, whose results are shown with the green lines for a variety of speech reception tests, including recognition of two-syllable words, recognition of keywords in relatively simple high-context sentences, recognition of keywords in lower context and more difficult sentences, and recognition of single-syllable words without any contextual cues at all. And this Northwestern University List 6 test of monosyllabic word recognition is the most difficult test given in standard audiologic practice. And you can see that the average scores range from relatively high to relatively low across these panels. But more importantly, the scores for each of the individual subjects show dramatic and very large improvements immediately with the application of the new processing strategy. So then we really trusted what the patients were telling us. Following these wonderful results, we wondered, well, how would more typical patients fare with lower levels of speech reception performance? And so we selected some subjects with typical levels of performance with their clinical devices, and their results are shown with the blue lines. And the wonderful surprise there was that they benefited at least as much as the high-performance patients with the new processing strategy. Well, this was wonderful. And the results were published in the journal Nature, and that article became They were published in 1991, and that article became the most highly cited publication in the field of cochlear implants in 1999, and has remained so ever since. Well, each of the companies did adopt this new strategy, thanks in large part to the improvement in performance, but also Mr. Herbert's policy of donating the results to the public domain. And each of the major companies utilized this and subsequently developed strategies by us and others in their implant devices. Results from one of the first clinical trials are shown in this slide, where in the left panels I'm showing recognition of keywords in everyday sentences in the top left panel, and recognition of the monosyllabic words that have no contextual cues in the bottom panel. And the circles indicate the scores for the individual subjects that included 55 postlingually deafened adult recipients of cochlear implants. So a couple of things to notice in these results are, first, that performance seems to improve over time. And here, and that there is a wide variability still in outcomes, but that variability narrows, at least for sentence recognition, with experience with the cochlear implant, such that more than 80% of the subjects are scoring more than 80% correct or higher on these relatively difficult sentences, in this case with about 1 year of experience with the cochlear implant. This is perfectly consistent with talking on the cell phone. This is perfectly consistent for a lawyer to be engaged in her practice. This is perfectly consistent with everyday communications in the workplace. And for many of these persons, if you didn't see the external parts of the device and didn't know them and were just conversing with them, you wouldn't know that they had a hearing problem. Astonishing. And it's so astonishing because we know how sparse and crude the representation is at the periphery, and yet somehow the brain is able to utilize this sparse input and utilize it progressively better over time, which is a little easier to see in the right panel, where I've plotted the means and standard errors of the means at each of these test intervals post-fitting. So I forgot to mention that in each of these columns, the scores show results for 1 month after the initial fitting of the device, 3 months, 6 months, 12 months, and 2 years. And the sentence test was administered at more intervals than the monosyllabic word test, which is why you see more points here for the sentence test than the monosyllabic word test. But the thing to notice is that you see substantial improvements in speech reception performance for both tests out to about 1 year after the initial fitting. This long time course of improvements implicates the brain as playing a principal role in producing outcomes with cochlear implants. Changes at the periphery, such as changes in the impedances of the electrodes or fibrous growth over the electrode array, would occur far more rapidly than this long time course. Instead, the long time course is consistent with what the neuroscientists call plastic changes in brain function. And so, in retrospect, it seemed that we just had to get above some threshold of quality and quantity of information to allow the brain to take over and do the rest. And by the rest, I mean 99% of the job. The prior processing strategies and implant systems probably didn't exceed that threshold or were just hovering around it. But with this improved representation, we exceeded the putative threshold for at least the majority of patients. How am I doing on time? Okay. So there has been a further improvement, and that is to provide stimulation in addition to that presented by a unilateral cochlear implant. And this can be done in the two ways that I described before. For combined electric and acoustic stimulation, the acoustic stimulus can be presented on the same side as the electrically stimulated side, the opposite side, or both sides, and the benefits are about the same among those conditions. And this graph provides an example of the benefits of this adjunctive stimulation for persons who have the residual hearing at low frequencies. Here, a comparison is presented between the Helms et al. Data that I showed you before for recognition of monosyllabic words, which has a mean score of about 55% correct, and these data were collected as late as 1997. This shows the results for fully inserted cochlear implants for 15 subjects who were studied in 2008, and you can see that there was no improvement in performance in that interval, despite developments in sound processing strategies and despite relaxations in the criteria for implant candidacy. In contrast, when the acoustic stimulus is added to the electric stimulus, you see a quite substantial improvement in performance. So for persons who have hearing at low frequencies, some residual hearing at low frequencies, this is a major advance. Similarly, stimulation on both sides with two cochlear implants can provide large improvements in speech reception performance and also can instate or reinstate a sound localization ability that's so important in listening to speech, for example, in a cocktail party situation. So the cochlear implant today is by far the most successful neural prosthesis in terms of restoration of function and number of people helped. And this graph shows the cumulated number of implant recipients over the years. And each of the dots represent a published data point. An exponential curve fits these data points with a correlation coefficient higher than 0.99. So the growth is purely exponential. And today, there are more than 450,000 persons who have received a cochlear implant. And if this exponential course continues, in less than 5 years, more than 1 million people will have received a cochlear implant. These numbers far outstrip the numbers for all of the other neural prostheses combined. And indeed, the cochlear implant has become a model for the development or further development of other neural prostheses, such as prostheses for restoration of vision, prostheses for restoration of balance, and so on. One thing we've learned is that a surprisingly sparse representation at the periphery can enable a remarkable restoration of function. At the beginning, we were focused on the complexities of the inner ear, but all of us missed the point. The point was that if we could just get enough information across, the brain would do the work. The brain could do the rest. I'll show you a very short video.
When I first started in practice in the mid-'80s,
All right, let me take a peek in here.
we didn't have anything to offer children who were born deaf.
When Walter was born, he was born deaf in his left ear. About the age of 2, he started losing the hearing in his right ear, and he lost it rather quickly.
I Doing good.
I'm so glad you came here. It's so good to see you.
For children born with profound deafness, receiving bilateral implants during their first years
I've been good.
You gonna sit next to me?
Yeah?
Yeah?
provide a life of hearing never dreamed possible.
Trains. Do you have toy trains like Thomas?
I like playing with toy trains.
It's made a big difference in his life. He's able to go to mainstream school. He's in a regular classroom. What would you like to say?
I like to say, I love you.
Why do you love Dr. Tucci?
I love her because she fixed my ears.
It's a privilege. It's a joy. You know, it's the biggest joy of my professional career to be able to do a cochlear implant in a child who can't hear and know that he or she will grow up to have normal hearing. It's a profound joy. This is really a miracle.
That's a segment from the Lasker video that Dean Katsouleas mentioned, and our own Dr. Tucci, who is head of the cochlear implant program here at Duke. Well, I got a lot of help over the years, and I would like to say that that help was essential to the progress that you've heard. And we have many people in the audience who are not shown in these pictures, but their contributions were equally as grand, and I am so grateful. Thank you for your kind attention.
Great job. Great job. If we could have the house lights up a little bit, I think we have time to take one or two questions before the reception, so wonderful. Any questions from the audience for Blake? I know that character.
Yes, so do I. Any questions? It's my great privilege. I'm such a lucky person to be here.
Is there any important difference in the mother language of the person speaking? Makes it easier or harder some languages than others?
That's such a wonderful question, and there has been some concern about a third of the world's population that use tone languages for communications. So phonetic differences can be conveyed by different tone contours, such as your voice pitch rising over the speech sound or your voice pitch falling over the speech sound. And one thing that is not represented as well with a cochlear implant as in normal hearing are these fundamental frequency contours. So there's been a little bit of a worry about that for persons speaking Mandarin, for example, using a cochlear implant. But the speech reception scores for sentence recognition and word recognition are just as good for these persons as they are for persons using German or English or other languages. So there are multiple cues in speech for each of the principal speech sounds, and maybe some other cues are used by these tone language users in making phonetic decisions. So we lucked out again. It works. Right, so that's a two-part question. A concern was expressed about implanting a very young child, and I think the concern is about changes in head size and bone growth and so on. and the other part of the question was about the wisdom of early implantation. Oh, reimplantation, yes. And so the other concern was if a cochlear implant has to be removed and then replaced, does that have any deleterious effects on the outcomes? The answer to concern number 2 is that no, you can replace a cochlear implant without producing any deleterious effects. Performance is just as good with the second implant as it is with the first. Of course, you don't want to put a person through another operative procedure unless it's necessary, but at least the outcomes are the same. In terms of implanting very young patients, there's almost a moral imperative to implant a child as soon as she or he is diagnosed as deaf, because the brain is capable of the most rapid and largest changes in function very early in life, up to about 2 or 3 years old. And if sound is reinstated in that early period, the child develops normally from a casual observation with perfectly normal hearing and can be mainstreamed into classrooms like Walter that you saw in the video, into normal classrooms. So you want to provide this input to the brain as soon as you know the input is missing. And another fortunate aspect is that the size of the inner ear is adult size at birth. So nothing is changing in the inner ear, and you don't have to worry about the electrodes drifting away from the target neurons or the electrodes being extruded from the inner ear. Everything is in place. And systems have been developed to accommodate the head growth between the position of the inner ear and the position of the implanted receiver stimulator. So these cables are coiled and flexible and can accommodate the growth of a child. So if everything goes as planned and everything goes swimmingly, a person who's implanted at 1 year of age can be using the same implant at 60 years of age. This is another beauty of the systems, is that all of the sound processing is done externally. And so if you have a nice electrode array implanted and you come up with a brilliant idea about how to improve the representation of sound with the implant, only the external components need to be changed. And in some cases, only the software and the little computer in the sound processor that sits behind your ear, only the software needs to be updated. That's the happiest outcome. Yes, in fact, we have, I think, in the audience a so-called single-sided deafness person who has normal hearing on one side and is deaf on the contralateral side, on the other side. And she and many others have now received a cochlear implant on the deafened side. And the tremendous benefit of that is reinstatement of sound localization abilities and re-entering the three-dimensional world. If you listen with just one ear, it's nearly impossible to localize sounds. You need the small timing differences and the small amplitude differences to infer the position of a sound. So if a sound is over here, the sound reaches this ear before it reaches this ear, and the sound is a little louder at this ear than at this ear. And the brain uses those cues to infer the positions of sound sources in the environment. Well, that's impossible if you have only one functioning ear. So people with this single-sided deafness condition who have received a cochlear implant typically use their cochlear implant all day, every day, and say that they would never give it up.
If I may, excuse me, use my purview as moderator to ask a question. And despite that I'm the engineering dean, I'm not going to ask a technical one. What I'd like to know about is the human response, reaction to hearing for the first time. Is there something you can share with us about maybe an experience you had with a patient? And what is it like for someone?
Let me show you another very brief video. It's just overwhelming to so many people who hear for the first time or hear again after being deaf or severely hearing impaired for many years. That video that you just saw has gone viral on YouTube and has been accessed more than 9 million times. What a great question. And it can be very difficult if an adult receives a cochlear implant who hasn't acquired language or is so-called prelingually deaf or was deaf at birth. So the brain has a massive rewiring job to do there. And results with such patients are not nearly as good as results from patients who became deaf after acquiring language. And this is the very reason why it's so important to get in early and provide sound input early for infants who are diagnosed as deaf, because then they get it right from the outset, and the brain is highly plastic and can make all these changes, and they perform beautifully.
Okay, well, I'd like to ask you to join me again in thanking Blake. This was an incredible journey, and thank you for sharing that with us and telling the story so well of an incredible innovation, something historic, and to be able to hear in person how it happened is a real treat and honor for all of us here. Please, all of you in the audience, would you join me again in thanking Blake Wilson?